Okay, so today's goal is to learn about sampling distributions for a difference in two different means or two different proportions, basically when we're looking at two different populations. So we're going to determine the shape, center, and variability of sampling distributions for a difference in both sample proportions and sample means. So again, many statistical questions involve comparing a characteristic in two populations. For example, if I wanted to know are males or females more likely to use TikTok? Which of two treatments is more successful for helping people to quit smoking? What is the difference between heights of 10-year-old boys and 10-year-old girls? So I want to compare two different populations or two different groups of some kind. So for example, suppose there are two large high schools, each with more than 2,000 students. In a certain town, at school one, 70% of their students did their homework last night, and only 50% of students at school two did their homework last night. The counselor plans to select a simple random sample of 100 students and record the proportion that did their homework, which would be p hat 1. And then school two's counselor will select a simple random sample of 200 students and record the population or proportion that did their homework, which would be p hat 2. And the question here is what will the sampling distribution of p hat 1 minus p hat 2 look like? And what does that even mean? So what does it mean to be a sampling distribution for a difference in proportions? So let's say we use software to randomly select 100 students from school 1 and 200 students from school 2, completely random samples. And then for each, or for both of those samples, we calculated the proportion from the sample who did their homework. So our first sample gave p hat 1 is equal to 0.72 and p hat 2 is equal to 0.47. So this was from school 1, this was from school 2. And the difference that we got between those two sample proportions, so 0.72 minus 0.47, is 0.25. And let's say we repeated that many times. So we end up with this little graph. This is our sampling distribution for differences of p hat 1 minus p hat 2 for a whole bunch of different samples. All right, this red dot right here represents the sample that I just told you about, where we found a difference of 0.25. But then we did this a total of 500 times. So what I want you to think about here is looking at this sampling distribution for means, what appears to be the mean of the sampling distribution, right? So kind of where is the center more or less, or what do you think would be the average difference in proportions? And what appears to be the shape? And then if you were to estimate standard deviation, what do you think that would be? So mean, I would say, is probably close to the middle, somewhere in this range. So maybe around 0.2. Our shape appears to be pretty symmetric. It's not perfectly symmetric, but it definitely has that general symmetric shape. And then so we would call this normal. It's a normal distribution, or roughly normal. And then it says if you were to estimate the standard deviation, right, remembering that on a roughly normal model, we should go out about 3 standard deviations each way to get to kind of the minimum. So if I imagine 3 standard deviations and what that might look like, that standard deviation distance is maybe around 0.06-ish, if I were to just guess off the top of my head. It's not a perfect guess, but I can kind of estimate just from that little graph. So let's actually look at what the rules are for sampling distributions of a difference in two proportions. The first thing is about shape. So it says as long as the individual population's standard sampling distributions are normal, then the distribution for the differences in sample proportions should also be normal. In other words, as long as NP and NQ, or 1 minus P, are greater than or equal to 10 for both populations, so as long as our kind of success-failure rule passes for both populations, for both groups, then our normal model is going to work for the difference sampling distribution as well. And then we have our formulas for mean and standard deviation. So our mean formula tells us that the mean of that sampling distribution of differences should just be equal to the two population proportions difference, right? So in other words, the mean of the sample proportions should just be equal to the population proportion, just like with single population data. And then it tells us our standard deviation formula, which is not quite as straightforward. There's a little bit more calculation involved, but basically we're taking, it's kind of the same formula as for a single proportion, we're just adding on the second population under that square root. So it looks a lot more complicated. So let's go back to our high school question and actually figure this out. So I'm going to start with shape, right? Our little rule said as long as NP and NQ are greater than or equal to 10 for both groups, then we know our sampling distribution for differences is going to be normal. So let's do that. Let's look at group 1, or school 1. School 1 had an N of, our sample size was 100. And then our P for group 1, so not P hat, but P was 0.7. So this is N1 and this is P1. So N times P for group 1 would be 100 times 0.7, which is 70. And then 100 times 1 minus 0.7, or Q, 100 times 0.3 would be 30. Both, so far, both greater than or equal to 10. For group 2, or school 2, our sample size was 200, so that's N2. And then for group 2, we had 50%, so P2 is 0.5. So now I'm going to do 200 times 0.5, which is 100. And then NQ would also be 200 times 0.5, because 1 minus 0.5 is 0.5, which is also 100. All of those are greater than or equal to 10. Tells us that our sampling distribution for the difference in proportions should also be normal. Yay, it's normal. So now let's look at the mean, right? Our rule says that the mean of our sampling distribution for the difference of p hat 1 minus p hat 2 is just going to be equal to proportion 1 minus proportion 2, p1 minus p2. So if I just look at p1 and p2, p1 is 0.7, p2 is 0.5. 0.7 minus 0.5 is 0.2. Yay. And then of course I used all my space, and now I have the longest, biggest formula left. So I'm going to actually see. Oh, cool. So I'm going to do, okay. So I'm going to come over here and do the standard deviation just because I ran out of room. So again, we're doing the standard deviation of p hat 1 minus p hat 2. So I'm going to plug in our formulas. So our formula says big square root. And then we're going to do, for group 1, p times 1 minus p over n, and then plus. And then for group 2, p times 1 minus p over n. So for group 1, p was 0.7 times 1 minus p would be 0.3, divided by the n for group 1, which was 100, plus. For group 2, p was 0.5, so 1 minus p would be 0.5, and then n for group 2 was 200. So I just kind of plug all those in, and then I'm going to use a calculator to figure out what that equals. So I'm going to do square root 0.7 times 0.3 over 100 plus 0.5 times 0.5 over 200 gives me 0.058-ish as a standard deviation. So there's my standard deviation for the difference in the two sample proportions for our sampling distribution. So I'll just put that here since I did the work over there. So if I compare that to what I had kind of estimated, right, it is roughly normal. I had said my mean looked to be around 0.2, which that was the mean we got from the formula. And then I had said the standard deviation looked to be about 0.06, just from like roughly eyeballing it. And the standard deviation was 0.056. So it actually worked out pretty well when we did the actual sampling distribution by taking repeated samples versus when we calculated it with our formulas. So that is how we find just kind of that general information for a sampling distribution for a difference in two proportions. So now let's look at one with means. So this is a new example. We're now talking about numerical data, so means. Based on info from the U.S. National Health and Nutrition Examination Survey, the heights of 10-year-old girls and 10-year-old boys are described below. So it says 10-year-old girls, the shape of that population distribution is roughly normal. The mean for that population is 56.4. The standard deviation for that population is 2.7. For 10-year-old boys, again, normal. Mean is 55.7. Standard deviation is 3.8. So at this age, boys are actually a little bit shorter than girls on average, and their heights are a little bit more spread out than girls typically. So suppose we take independent random samples of 12 girls. So our sample size for group 1, which is girls, is 12. And then 8 boys. So our sample size for group 2, which is boys, is 8. And then we measured their heights for the sample. So what would this sampling distribution of x bar g minus x bar b, so instead of 1 and 2, we use g and b, look like? So again, we have to imagine if I were to take many random samples. So this says we use software to randomly select 10 or 12 10-year-old girls and 8 10-year-old boys independently. Our first set of samples gave us a mean for girls' heights of 56.09, a standard deviation of something. And then the x bar for boys was 54.68 with a standard deviation of something, resulting in a sample difference of 56.09 minus 54.68, so about 1.41 inch difference. So in the sample, the girls' average was 1.41 inches taller than the boys. So suppose we repeated this process 1,000 times. So we end up with 1,000 samples of 12 10-year-old girls, 8 10-year-old boys, found the difference in the sample height. So again, we have our graph. That red dot right there represents the sample difference that I just talked about. But then we did this a total of 1,000 times. So again, we're going to think about what appears to be the mean, what appears to be the shape, if you had to estimate the standard deviation. So if I looked at this one, I would say overall roughly normal. The mean again is probably around the middle-ish, so maybe around 1 inch of difference, more or less. And then our standard deviations, again, if I think about from the mean to the minimum, or you could do it the other way from the mean to about the maximum, should be about 3 standard deviations either way. So if I just kind of eyeball trying to split that up into 3 sections, we can get a rough standard deviation. It's kind of hard to tell in this one how long that distance is. Maybe 1.5-ish if I were to guess, somewhere in there. Again, we're just rough estimating, and this is not really typically something you have to do a super important estimate on a test, but we're just kind of practicing. So just estimating the looks of it. So let's look at our rules. So just like with proportions, basically our rule for shape is as long as the individual sampling distributions are normal, then the population of differences should also be normal. So in other words, as long as either both populations are given as normal, or the sample sizes for both samples are greater than 30, or one population is given as normal and the other sample size is greater than 30. So you can kind of mix and match. But remember, there were 2 ways of testing whether a sampling distribution of means is roughly normal, and that is either the population is given as normal or the sample size is greater than 30. So as long as one of those things is true for both populations, then our sampling distribution of differences is going to be normal. And then our formulas are telling us the mean of the sampling distribution is just the 2 population means subtracted. And then the standard deviation, right? Again, it's very similar to our standard deviation for single populations. We just kind of have to add them together, and because of the way that it works with standard deviation, we kind of looks a little different. But this is our formula right here for standard deviation. So standard deviation squared for group 1 divided by sample size for group 1 plus standard deviation squared for group 2 divided by sample size for group 2. So let's go back to our example and calculate our mean, shape, and standard deviation. For shape, both populations were told to us to be roughly normal, so that we know our shape is definitely going to be normal, since we were given that both populations. Our sample sizes, if you remember, were 12 and 8. So if we were not given a population for both groups that was normal, these would not be big enough sample sizes for our sampling distributions to be normal. But luckily we were given that population. Mean, all right, our mean formula, I'll do mean up at the top here. So mean of x bar g minus x bar b would basically just be the means of both subtracted. So I'm just going to take the population mean right here. So 56.4 minus 55.7 is 0.7. So the mean of that differences sampling distribution should be about 0.7. Right? And then our standard deviation of the differences says we're going to do square root of standard deviation of group 1 squared over sample size for group 1 plus standard deviation for group 2 squared divided by sample size for group 2. So if I plug in that info, for group 1, standard deviation was 2.7, this is the girls, squared over sample size for the girls was 12, plus standard deviation for boys was 3.8 squared over sample size for boys. Put that in my calculator, clear that out. So I already forgot. 2.7 squared over 12 plus 3.8 squared over 8, all under a square root, gives me 1.55 as my standard deviation. And again, just to compare to what I guessed, I had guessed the mean was around 1, so I was a little off on that. Again, it was just eyeballing. My guess for standard deviation was about 1.5, which is pretty close just from eyeballing. And again, my shape is definitely very normal. So that is how I deal with sampling distributions for a difference. From that information, once I know the shape and the mean and the standard deviation, I could of course find a z-score and find a probability for a specific sample difference. So if I wanted to know, what are the chances that I get this specific sample difference or higher, or that specific sample difference or lower, I could then go on and find a z-score. So I could say like 1.41 minus the mean was 1.7 divided by standard deviation was I already forgot, 1.55. And I could find a z-score and I could find a probability using the same method. We don't see a whole lot of this particular lesson on AP exam, but I at least wanted to kind of talk through those formulas that are on the formula chart and how we would use them if we were given a problem like that. So that is it for this lesson. See y'all next time.